In this video, we'll be closing out our review of hypothesis testing, starting with the t-distribution, which we'll use when the standard deviation of the population is unknown, just like with the confidence intervals when we use t instead of z. Recall that t-distribution has n-1 degrees of freedom, that this is the additional component that's added on to the z distribution. And I should mention real quick, this equation looks exactly the same. I think I mentioned this in the previous video that all that changes is the z changes to a t in our test statistic notation, and that because we don't have the population standard deviation, we're going to use an estimate using the sample standard deviation. So the p-value approach is actually exactly the same as before. So is the critical value approach. I will say that we have to use a different set of distributional tables for the critical value approach than we did when the population standard deviation was known. So we're going to be using the t-tables instead of the z-tables. But the p-value, especially if we're using software, doesn't change at all. The interpretation is exactly the same. Incidentally, this highlights one of the benefits of the p-value approach and why in applied and practical research, the vast majority of individuals use the p-value approach as opposed to the critical value approach. And it is because once you learn how to interpret p-values for one context, the interpretation largely stays the same across a whole array of different statistical tests. So anytime you see a p-value given by a computer output, you can typically interpret it the same way. What you need to know is the null and alternative hypothesis, but after you know that, you can use the p-value to determine which of those hypotheses you're going to stick with, the null or the alternative hypothesis. So using a distributional table for p-values, again, I mentioned earlier it's annoying. Actually, with the t-distribution, it's impossible to get an exact value. What you can get is a range of values. So I don't use p-values for me. If you're doing it by hand, I think it's easier on you to do a critical value approach than a p-value approach. But if you're using computer software, p-values are pretty easy to do and are the default output. Actually, they'll by default provide both the test statistic and the p-value. They don't by default for most computer software packages that I'm aware of. They do not provide the critical value typically. So you, for your hypothesis tests, tend to lean on p-values when you get into using computer software. All right, so if you want to give this one a shot, please feel free. Go on and pause the video and give this problem a try. All right, so coming back, we've got a sample, we've got a mean speed, we've got a standard deviation. Now this is important. The standard deviation is coming from the sample. The sample shows a mean, so that's a sample mean, and a standard deviation. So this is a sample mean, a standard deviation. This is how I know I'm in a sigma unknown case. I'm going to use alpha equals 0.05, and they're looking to see if vehicle speeds are less than 65 or bigger than 65 on average. All right, so I developed my hypotheses. The null is less than or equal to 65. The alternative is greater than 65. I've got my level of significance. I've got my test statistic value. And again, we'll plug these values in the same way. I will say one thing I love about t, and why personally I almost always use t instead of z, is because when I'm dealing with real data, I never know the population standard deviation. So I have to calculate the sample standard deviation. This equation is what I use because it uses the sample standard deviation instead of the population standard deviation. We have changed in this minor change from needing someone to tell us an additional piece of information, which is what we needed when we were using the z distribution, moving to a place where you can just hand me a data set and I can do the rest myself. So this is a really, really, really significant shift in our ability level. Both with confidence intervals, we didn't really highlight as much with the confidence intervals, but it's true with the confidence intervals, and it's true here. So this is really important. I really want you to internalize this a bit, that this shift is the shift between needing my teacher to tell me something or not actually being able to use this in the real world, because my client sure as hell is not going to have any idea what the population standard deviation is, to now being able to just be able to now being able to be handed a data set and do everything else yourself. So this is actually a really, really meaningful shift in your ability level that I just wanted to pause and acknowledge here. So for the p-value approach, I'm going to be looking on this table and I'm going to be trying to figure out, okay, well, where, so I've got my test statistic, t equals 2.268. Where does that statistic fall for the particular degrees of freedom? So I've got my degrees of freedom level, 63, so I'd round down to 60. And then I've got my vertical bars that say, okay, these are the probabilities. So I'm looking for where does this fall in relation to the other t-values, and recall that in the t-table, the t-values are in the table. In the z-table, the probabilities were in the table, the t-values were out, or the z-values were outside. In the t-table, the t-values are in the table. So what I find is, well, this 2.286 is bigger than 1.998, which is the 0.025 value, but it's smaller than the 2.387, which is a 0.01 value. So the p-value is somewhere in between those because my t-value is somewhere in between those. So that's how we would come up with a range for the p-value using the t-table. It's really awkward. I don't like it. And again, software, we can compute this exactly. If we wanted to hand compute it for a problem like this, we can directly take the test statistic and compute the p-value. But in software, honestly, if we give it a data set, it'll automatically do that for us and go ahead and calculate the p-value. In any case, because the p-value is within this range, I know that even if it's as big as 0.025, it's still going to be less than 0.05. So because of that, I can go on and reject the null hypothesis and say that there is enough evidence to make the claim that there is a statistically significant difference between the mean speed of vehicles and this 65 miles per hour. Specifically, the mean speed is greater than that. And I'm at least 95% confident in this particular conclusion. All right, now for the critical value approach, we're going to do exactly what we would normally do with a critical value approach. We have to find the critical value and make a decision. So in this particular case, we have our degrees of freedom at 63. We look up the t-value appropriate to the 0.05 cutoff for a one-tailed test, so 0.05 in a single tail. Excuse me, that's going to be 1.669. And then we're going to reject, because it's a greater than test. We're going to reject if the test statistic is greater than this value. If it were less than test, we'd reject if it's less than the negative version of that value. So we determined whether to reject the null hypothesis. Because the test statistic is greater than that value, we do reject the null hypothesis, and we can say that we have enough evidence to believe that the mean vehicles is greater than 65 miles per hour. And if you ask me how confident I am in that decision, I'd say, well, I'm 95% confident. Now, this is actually a great highlight for where the difference between practical and statistical significance comes in. So I'm going to rewind a bit here and go back to what we calculated the mean speed of these cars to be. The speed limit is 65. We calculated the average speed to be 66.2 miles per hour. We're talking about, is this a good location for a radar trap? One of my questions for my client might be, well, at 66.2 miles per hour, are you going to pull anybody over if somebody's going 1.2 miles per hour over the speed limit? Is that enough? And actually, that's kind of a fun way to, and perhaps a better way to conduct hypothesis tests, is not to do the cutoff at 65, but to do the cutoff at a value that is meaningful. So in this case, 65 is a speed limit, but if you're not going to pull anybody over for going 66 miles per hour, well, then at what point are you going to pull somebody over? And then we can do this test again to figure out, are people going faster than your cutoff level or not? Because in this case, I would argue, and I'm not a police officer, but I think most officers are nice enough to not pull me over if I'm going 66 miles per hour or 66.2 miles per hour. So again, this goes into the distinction between practical and statistical significance. We have a statistically significant difference in this case. As to whether we have a practically significant difference, honestly, it's a judgment call. And who do I trust to make those judgments? Well, I would trust somebody who's an expert in the field. And in the case where I'm working for someone else, if I'm working for a boss or a client, the person I trust is the boss or the client. I simply have this conversation with them and say, hey, this is what's going on. There definitely is a difference, but I don't know if the difference is big enough for you to care about. And the idea that we have a good amount of evidence that there's a difference. I shouldn't have said definitely. We don't have any definites. We don't prove anything. We just have evidence. But if we have evidence that there's a difference, again, there's a distinction between having that evidence and having evidence that that difference is meaningful. So in this particular case, you can see here's the rejection region. Here is the particular t-value for the test statistic, and the t-value for the test statistic falls within the rejection region. I'm not going to play the p-value games with the t in the table. I think your homework may have you do a couple of these just to prove that you can. But honestly, after you get through this assignment, we should never revisit this. It'll always be done via R so that you can calculate it directly. All right, so population proportion follows exactly the same thing we've been doing. Nothing has changed. The test statistic, we have the same. And notice, actually, I don't think I mentioned this earlier. Yeah, let's talk about this. I discussed that the confidence intervals and hypothesis tests were directly related, but I don't think we ever talked about how this is. This is our point estimate. Is this first value? Actually, the whole top's our point estimate, but we won't get into that. This bottom component is our standard error. And then we compare to a critical value. So when we compare to that distribution, we compare to a critical value. So what we have is the point estimate divided by the standard error compared to the critical value when we're working with hypothesis tests. And then if we're working with a confidence interval, we have the point estimate plus or minus the critical value times the standard error. This just to illustrate that when I say that doing a hypothesis test with confidence intervals aligns with doing a hypothesis test according to this approach, I don't mean like arbitrarily or hey, luck of the draw. I mean they literally use mathematically identical components, and not like mathematically like we have to do this long derivation to prove they're identical. Like, hey, I can see this exact symbol in my confidence interval equation. Hey, I can see this exact square root in my confidence interval equation. Hey, I can see this exact critical value in my confidence interval equation. So these really are just using the same things, just put together in a slightly different way. Incidentally, it's another argument as to why some people prefer confidence intervals over hypothesis tests, is because it really has the same information, but confidence intervals may combine this in a way that shares more of that information. The conclusion for a hypothesis test is yes or no. The conclusion for a confidence interval is a reasonable range of values. So what would you prefer? A reasonable range of values where you can make your own conclusions about yes or no, or just a yes or no answer? And the answer is both of these have their place. But for someone who's been trained in this, having the range where you can make a yes or no conclusion about a different variety of potential null hypotheses may be more extensively useful. Also, don't forget that one case that we had in a previous video where we had the bottom of the range was very, very close, and we get into the discussion of statistical significance and practical significance, which if I'm just given a yes or no answer, I don't have enough information to investigate that question for myself unless the person who gave me the yes or no answer brought it up. But if I have the confidence interval, I can actually make those ask those questions and investigate that at least a little bit by myself. All right, so we have the same rules as the confidence interval, that is n times p and n times q, or n times 1 minus p needs to be greater than or equal to 5. Again, just to make sure we have enough data and that the p is not right at the edge of the probability. Notice that with proportions, we use the z-scale, so the cutoffs for the z's are exactly what we talked about. They are the exact same thing as the cutoffs for the z's when we had the test for the mean when the population standard deviation was known. So that's what we're using here. And then the p-value approach is exactly the same. And again, this is the very nice thing about the p-value approach. I don't have to worry about the distributions, especially if I'm using software and giving it data where it automatically spits out the p-value for me. If I'm calculating it in a software, if I'm calculating this by hand, I still have to know the distribution it comes from because I have to tell the software how to calculate it. All right, well, I hope everybody by now should be able to give this one a shot on their own. So pause, give this problem a shot, and then we'll come back and see how you did. All right. So coming back to this, we see that we're looking at this predicted estimate and seeing the percentage of these accidents that were caused by drunk driving. Now we take a sample of these accidents and we see that this number of these samples was caused by drunk driving, and then we want to use this to test the claim. Now when we're testing a generic claim, I'm not testing if this is greater than or less than. I'm just testing, is this right? Is this 50% number correct or not correct? So because of this, my hypotheses are going to be equal to, that's the original claim, and then not equal to. So is that correct or not correct? So it'll be a two-tailed test because we have this not equal to here. Greater than would be a one-tailed in the upper tail. Less than would be a one-tailed in the lower tail. All right, specify the level of significance, 0.05. Compute the value of the test statistic, sigma sub p. So this is our standard error. We talked about that before. This is everything in the denominator of the test statistic. So once we have that, then, so this is kind of a weird construction now that I'm looking at this. But once we have this, we have everything in the denominator, and then we have the numerator that we're working out. And typing all this into our magic box, we get 1.28 as our z-value. So using the p-value approach for 1.28, we would look, we've got our curve, we've got 1.2 at the top. Now it's a two-tailed test, so I'd find the area more extreme. So more extreme would be further away from the middle, so on the upper end. So I'd find that area. That area would be about 0.1003. And then I would multiply that by 2 because this is a two-tailed test, and to account for the fact that it could have been on the lower end too. So my 1.003 multiplied by 2 gives me 0.2006 for my p-value. Using this cutoff level of 0.05, I find that this p-value is above 0.05, and we fail to reject the null hypothesis. So all we would say is we don't have enough evidence. Now, this is not evidence to support the claim that this is 50%, right? This is not saying we have evidence for the null hypothesis, not evidence to support the claim. This is we don't have evidence that it is different than the claim. We were trying to find evidence that it's different. We didn't find that. So that's a really important distinction. We declare not guilty. We don't declare innocent. So in this case, again, we don't have evidence that it is 50%. We just didn't find evidence that it was different than 50%. All right. So for the critical value approach, I cut my alpha in half. And again, it's because this is a two-tailed test, so I want a cutoff on the top and the bottom. And again, outside of those cutoff regions are going to be where I get significance. So I compare, I've got negative 1.96 and positive 1.96, so I guess I'll draw this out real quick. In my very terrible drawing, I apologize. So we've got negative 1.96 on the left, positive 1.96 on the right. So 1.278 falls like right here on that. So under the top cutoff and not below the bottom cutoff, falls kind of right here. So I can see that it's in the region of do not reject. So we fail to reject the null hypothesis. And again, this is to say we don't have enough evidence to make this claim at the 95% confidence level. Now, before we're done, I do want to call out one thing. If I were going to make this claim at the, instead of the 95% confidence level with alpha equals 0.5, if I wanted to make this claim at the 70% confidence level, like that's a really low confidence. But if I wanted to do that, alpha would be 0.30, the p-value would be below that, and I could make this claim at the alpha equals 0.30 at the 70% confidence interval. I could say we have enough evidence to make the claim that it's different at the 70% confidence level. What is this to say? This is to say two things. First of all, always set alpha before you look at your data. This should be set first. And if you don't, it should be set to 0.05 as a standard. You need to have a very good reason to change this. Because if I ever saw a paper where somebody said 0.30, I would anticipate that something like this happened. That they looked at their p-value, they said, okay, how high does alpha need to be for me to still claim that this is statistically significant, and then let me change alpha after the fact. That is extraordinarily bad practice and considered to be unethical statistically. So that's the first thing, set alpha first. The second thing, item number 2, is that the conclusion depends on the confidence level. Notice that if I set alpha equals 0.30 first, then my conclusion would be statistically significant. There is enough evidence for a convincing difference between the two. What does this mean? This means that the significance level plays an impact on the level of evidence necessary to make a particular conclusion and has a very real impact on which direction we choose to conclude. So it's important to set this. It's important to set this at a right value, at something that's reasonable. Don't go artificially high or artificially low. It's important to set it at something that's reasonable. If you go artificially high, 0.40, people just aren't going to listen to you because you're not very confident in your claims. If you go artificially low, 0.0001, you're going to have very rare situations where you would be able to make these claims, even if there would be a pretty decent amount of evidence to support them. So it's important to set these alpha values at something right. Again, set it good, or set it initially, set it before you look at data. That's point 1 here. And point 2 is take some time to figure out a good level to set it. And if you don't know, 0.05 is a good one because alpha does have an impact in your conclusions. All right, ladies and gents, thank you for suffering through our stats boot camp with me. This has been a pretty long set of video lectures that are all crammed together as our review of previously seen stuff. I tried to take some time to go over some of the things I felt to be most important, but I did go relatively fast. Again, we had just, I don't know, maybe 5 or 6 videos that covered if it's a class with me, almost half a semester's worth of content that we're going to be doing in a week or two. So this has been quite a lot. Please do feel free to reach out if you have any questions at all. Let me know. You can send me an email or get in touch on our learning management system. In the next video, we'll be talking about how to implement some of this stuff in R and kind of getting up to speed on, well, how can we do some of this that way? Because R is going to be a tool that we'll be using for the rest of class. So please reach out if you have any questions, and if not, then please check out the next video.